Hi, and welcome to another exciting and interesting video on engineering machinery. Now in this video we're going to be talking about the shell and tube heat exchanger. Some of you might think you know a lot about shell and tube heat exchangers, and that's fine. Then you can watch this video and it will just reinforce what you already know. Some of you might not know anything about shell and tube heat exchangers, and that's also fine because you're going to learn a lot in this video. We're going to look at all of the main components that make up a shell and tube heat exchanger. I'm going to show you some of its design features, its advantages and disadvantages, and I'm also going to show you how it works. So let's get started. Now this is not how a shell and tube heat exchanger normally looks in the workplace. If it was, it would be a lot easier to understand how it works. So let's reset the configurator tool for a moment, and now you can see the shell and tube heat exchanger as it would normally be in the workplace. There are different designs and variations, but this one here is quite standard. So let's start by looking at the outside of the heat exchanger. We've got the shell. It's a pressure vessel, which means it's going to be pressurized to match the fluid or the system pressure that's flowing through it, or specifically flowing through the shell. Sometimes people refer to the shell also as the housing. We've also got a front and a rear of the heat exchanger. Other than that, we've got four main connections to the heat exchanger. 1, 2, 3 and 4. We have 2 inlets and 2 outlets because we have 2 fluids that are flowing into and out of the heat exchanger. This heat exchanger is called a shell and tube heat exchanger because it has a shell and because within the shell there are some tubes. Let's take a cross section and we can now see exactly what's happening inside the heat exchanger. So we have a tube side fluid. The tube side fluid enters here and is discharged here. We have a shell side fluid which enters here and goes along here and is discharged here. The reason we call the tube side fluid is because it flows through tubes. You can see it comes into the heat exchanger, and once it enters this area it has to flow through these tubes because it's the only place it can go. Once it flows through the tubes, it's going to get to the other end of the tubes. These tubes are just straight tubes. The fluid comes out on the lower section here and re-enters in the top section here. When the tube side fluid re-enters through the top section of these tubes here, it's going to flow again in a straight line to the opposite end of the heat exchanger, and it's going to come out here and then going to be discharged or exit the heat exchanger through the outlet. That is the flow path of the tube side fluid. The shell side fluid enters the heat exchanger here, and then it comes through and it will pass through a series of baffles, which we'll take a look at in a moment, and it's going to be discharged through the shell side fluid outlet down here. So tube side fluid in on the lower left, along here, straight flow, up, back the other way and then out. Shell side fluid down through here, past all the baffles and then out on the lower right hand side. Although I refer to fluids in this video, sometimes it's a little bit easier to think of them as flowing mediums. I say that because doctors say you should drink a lot of fluids, but realistically a fluid can also be a gas. Let's have a look at the tube side flowing medium in a bit more detail. What I'm actually going to do, I'm going to remove everything but the tubes so that we can focus on those first. So here are our tubes. The tubes are collectively known as a tube stack or a tube bundle. For example, the upper half of the tube bundle would be all of the tubes above this row here, and the lower half of the tube bundle would be all of the tubes below this row here. So that is our tube bundle or tube stack. In order to hold the tube bundle in the correct position, we're going to use baffles, tube sheets and also tie rods. Let's add the tube sheets first. These are our tube sheets. The tube sheets are used to first hold the tubes in position and secondly to seal the inside of the shell so that the shell side fluid stays within this space between the two tube sheets. So here's one tube sheet, sometimes known as the rear tube sheet. Here's the front tube sheet, and the shell side fluid is going to remain in this space. So that's the pressure boundary for the shell side fluid. We want to fix the tubes in position using more than just 2 anchor points. So we'll use baffles as well. And the baffles just add some extra support to help keep the tubes in alignment. You'll also sometimes see tie rods, and the tie rods are used to connect the tube sheets or the baffles together, which again adds structural support to the tubes. Within the tubes, what you're actually going to have are turbulators or tube inserts. You'll push the tube inserts into every one of these tube holes. So for example, we'd push a tube insert in here, or a turbulator, and that turbulator is going to create turbulent flow. This turbulent flow helps increase the heat transfer capacity of the heat exchanger, and also helps us keep the inside of the tubes clean. We reduce the likelihood of deposits building up on the inside of the tubes because we have turbulent flow rather than laminar flow. So that's everything related to the tube side fluid. Let's load up some parts now so we can have a look at the shell side fluid. Now we've already discussed the tubes, so I think we can remove those. And we can see now exactly what's happening with the shell side fluid. The shell side fluid is entering through here, it's going round the baffles, and then it is being discharged here. We can see that around the tubes there is space for the fluid to flow because the tubes are not all directly next to each other. There's a bit of a gap. You can see here, if I come across, all of these gaps where my mouse is going now is where the shell side fluid is going to flow around the tubes. We want to have turbulent flow, the same as what we had in the tubes, and in order to get that we use the baffles. So the shell side fluid comes in here, flows around the tubes. Because of the baffles, it will exchange heat with the fluid within the tubes, and then it's going to drop out of the shell side fluid outlet here. Once again, this turbulent flow increases the heat transfer capacity of the heat exchanger, which makes it more efficient, but also helps us prevent or reduce the likelihood of deposits building up on the outside of the tubes. Let's load up another 3D model so I can show you a slightly different design of a shell and tube heat exchanger. So here is the first design that I want to show you that's slightly different from what we looked at before. You can see that externally it looks pretty much the same, but if I show you the tubes and we reverse that around, you can see that the tubes themselves are no longer just straight. They're actually rounded into a U shape. This is actually called a U-type shell and tube heat exchanger. The tubes have this U shape. Let's load up a more simple design because I just want to explain to you what a one-pass and a multi-pass heat exchanger is. So here we have a heat exchanger without a header or a bonnet. And if we take away the shell, in fact what we can do, we can actually just take a cross section. You can see that this time the tube side fluid comes in here, flows through the tubes and exits on this side here. So in on the right, out on the left. And what's interesting about this particular heat exchanger is that the tube side fluid represents a single pass of the heat exchanger. You'll often hear people referring to heat exchangers as either single or multi-pass. The shell side fluid has a multi-pass design. It's passing multiple times over the tubes. The tube side fluid does not have a multi-pass design because it's travelling directly through the tubes and then out. If the tube side fluid was to come in from the right, come out on the left, and then go back around and then exit on the right, then this would be a multi-pass design, because it too would be passing through the heat exchanger multiple times. This heat exchanger would be described as a multi-pass heat exchanger just because the shell side fluid, or one of the fluids, is passing multiple times over the other fluid. If the shell side fluid came in from the top and dropped out of the bottom with no baffles, then the shell side fluid would have a single pass design, and so would the tube side fluid, and we would say this is a single pass heat exchanger. That's actually quite rare though, you don't see that very often because it's not very efficient. If you ever look at steam condensers though, you will see that design, and generally whenever you convert a vapor into a liquid or whenever you're changing the state of something, you'll often use a single pass design. People also talk about counterflow, crossflow and parallel flow. This particular design is a counterflow design because the tube side fluid enters on the right and exits on the left, and the shell side fluid enters on the left and is discharged on the right. So they're flowing in opposite directions to one another, right to left and left to right. That is a counterflow design. It is the most efficient type of flow design you can have for a heat exchanger. If the shell side fluid came in on the right and exited on the left, then we'd have a parallel flow design because both the tube side fluid and the shell side fluid are flowing from right to left. If the shell side fluid came in at the top and was discharged straight out of the bottom, this would be a cross flow design because the fluids are flowing at a 90-degree angle relative to each other. So different flow designs depend on what you want to use the heat exchanger for. Let's have a talk now about some of the advantages and disadvantages associated with this type of heat exchanger. When we talk about advantages and disadvantages associated with the shell and tube heat exchanger, we're often comparing it to the plate heat exchanger because in the industrial world we're either using plate heat exchangers or shell and tube heat exchangers. Normally. There are some other designs, but those two are the most dominant within the industrial engineering world. Now, shell and tube heat exchangers are relatively cheap. They have a simple design and they're quite easy to maintain. They're also suitable for higher pressures and temperatures compared to plate heat exchangers. The pressure drop across a shell and tube heat exchanger is less than that of a plate heat exchanger. It's also easy to find and isolate leaks in the tubes compared to trying to find and isolate a leak in a plate heat exchanger. Shell and tube heat exchangers also don't foul as easily as plate heat exchangers because they don't have the very fine clearances that a plate heat exchanger has. There are, however, some disadvantages. They're less efficient than plate heat exchangers. They also require more space to open and remove the tubes. And you can't increase the cooling capacity of a shell and tube heat exchanger. With a plate heat exchanger, you can simply add more plates or remove plates in order to vary the cooling capacity. With the shell and tube type heat exchanger, this is not possible.